Design and analysis of 3D scanning system for scanning an object. Abstract 3D scanning is gaining its popularity in this new age technology, Industry 4.0, since it is the process of analyzing a real-world object or environment to collect data on its shape and possibly its appearance. The collected data is then utilized to construct digital 3D models in CAD software. This technology is used in augmented reality, motion capture, gesture recognition, robotic mapping, industrial design, reverse engineering, prototyping, quality control, inspection and the digitization of cultural artifacts. This paper introduces a mechanism to construct a 3D scanner that is convenient to use and handle. The object held between 2 point supports is scanned by Intel SR300 laser scanner with the help of a dolly mechanism. Data points collected by the scanner are converted into an STL file in 3D sense. These points can be imported and optimized using the Function Generative Design app of 3D Experience platform, a Dassault Systemes platform, 3D PLM. Keywords: 3D scanner, data points, reverse engineering, dolly mechanism, 3D modeling and simulation. Introduction. The first 3D scanning technology was produced in the 1960s, and since then it has improved in terms of accuracy, time, and effort. The scanner is mounted on a dolly mechanism. This is a wheeled cart or similar device used in filmmaking and television production. A motorized dolly mechanism is used ensuring smooth motion and getting accurate points from the scanner. The laser scanner calculates the time taken by laser from emission to the reception, and the sensor gives geometrical information of the object. The distance of the object is calculated with the information of time. The scope of this paper is to create a mechanism for a 3D scanner that scans any rigid object sizing between 50 mm x 50 mm x 50 mm and 300 mm x 300 mm x 300 mm. 2. Literature review. Various 3D scanning methods suggest that to scan the object it should be held stationary and the camera should revolve around the object. After experimenting with the Intel 3D scanning camera, it is found that a speed of 1 rpm is optimum for scanning the object. The position of the camera plays an important role in scanning, as the camera angles have to correct to scan the maximum area of the object. In a conference paper by Ala Abdirahim, the author has proposed a mechanism for 3D scanning which involves the object being stationary and scanner rotating around it. This design, however, doesn't cover the base resting on the table while scanning the object. This drawback can be overcome by clamping the object at 2 points, leaving rest of it exposed to the camera. A market survey. There were few scanning mechanisms available in the market. 1. First model. The object to be scanned is held in between 2 point supports. It is rotated about a vertical axis. The camera is placed stationary at the side with adjustable mounting. When the object is rotated, the camera captures the surface of the object. Advantage: more surface is exposed to the scanner. Disadvantage: difficult to rotate object between 2 pointers, due to inertia. 2. Second model. The object to be scanned is kept stationary on a table. The camera has a mechanism to revolve around the object to scan the surface. Advantage: easy rotation of the camera. Disadvantage: cannot capture all the data points. As the object is mounted on the table, it is not possible to capture the lower data points of the body. There may be cavities or holes in the object at the lower part, which might be important to be captured. 3. Third model. This mechanism is a hybrid of the above mechanisms. It has the concept of supporting the object at 2 points from the first model and the concept of revolving the camera around the object kept stationary from the second mechanism. A dolly mechanism is introduced to revolve the camera in a circular track. 3. Design calculations. Design calculations were done using the book Design of Machine Elements by V.B. Bhandari as reference. The maximum size of the object equals 30 x 30 x 30 cu.cm. Considering maximum weight of the 300 kg I.EF equals 3 knots. Material properties, Design Data Book. Material equals Fe620, E equals 200 GPa, SYT equals 380 MPa, SUT equals 620 MPa. A. Designing the lower pointer. The weight of the body scanned is supported on the lower pointer. Lower pointer is designed for crushing. This is the minimum diameter of the lower pointer, support. This pointer is to be checked for buckling. For frustum. To get the dimensions of the frustum, Rankin's theory is utilized. Iterations are made assuming different dimensions of height and diameter of frustum, and buckling load of the same is calculated. To find moment of inertia. D1 equals smaller diameter. D2 equals larger diameter. H1 equals height of the frustum part of the pointer. H2 equals height of the cylindrical part of the pointer. This is the minimum diameter required for the external flute. Hence, our assumed dimensions are safe. Weight of the pointer equals 10 N, negligible, material, Fe620. Threading will be required at the bottom of the upper pointer and inner flute. Pitch equals 1 mm, outer diameter, do, equals 20 mm. Thickness, T, equals 2 mm, inner diameter, D, equals 16 mm. C. Designing pin between the flutes. Total weight acting on the pointer is self-weight and clamping force applied. Therefore, weight equals 10 N. The pin will shear between the inner and outer flutes of the upper pointer. Assuming the diameter of the pin equals 7 mm, total length of the pointer L equals 400 mm. 1. Design for shearing. Equals 0.1299 MPa. This is forces less than the actual applied shear force, 95 MPa, hence design is safe. D. Dimensions of the inner flute of the upper pointer. Core diameter, DC, equals 15 mm. 7 holes of 7 mm diameter will be drilled on both inner and outer flute as shown in the figure. Figure 6. Upper pointer. E. Dimensions of the upper pointer. D1 equals 5 mm, D2 equals 12 mm, H1 equals 20 mm, H2 equals 60 mm. Figure 7. Upper pointer. The platform will rotate along the rails. It will carry the load of motor, camera, scanner, platform, itself, and the connecting rods. These components approximately weigh 10 kg. Weight equals 100 N. Thickness equals 15 mm. As per the scope of the project, the small object measures equals 5x5x5 cu.cm. For small object, the diameter of the rails is 1 meter. The maximum distance the camera will be placed away from the rails is 40 centimeters. This distance will not exceed as the radius, 50 centimeters, and the camera will be unable to scan the object which is near than 10 centimeters. Hence, the moment will act on the rails in the inner side of the rail. Inner moment equals 400 mm, x 100 n, equals 40,000 nmm. For big object. When the object is of bigger size, the camera needs to be placed away from the rails. The maximum distance the camera will be placed away from the rails is 10 centimeters. Moment equals 100 mm, x 100 n, equals 10,000 nmm. Carriage, IS equals x 153 x 150 equals 42,187.5 mm4. EI equals 1503 x 15 equals 421,8750 mm4. I equals IS plus EI. I equals 42,187.5 plus 421,8750 equals 426,0937.5 mm4. The frame is fixed so no moments and shearing occur. Dimensions, 150 x 150 x 15 mm3. Figure 8. Stepper motor. Power of motor P equals 7 watt, weight of system on carriage equals 5 kilograms. F equals 5x 9.81 equals 50 N. Force on each wheel equals 25 N. Assume D2 equals 0.05 m, diameter of driving wheel. Now, using velocity ratio formula, 2 cm extra is taken for rubber stopper. So, equals 15 rpm. F designing belt. Using basic power equation, P equals 1.308 W. Selection of flat belt from manufacturer's catalog. The maximum power transmitted by belt equals kW, max equals Fa kW. Where kW, max equals power transmitted by the belt for design purpose. kW equals actual power transmitted by the belt in a given application. Fa equals load correction factor. Now, load correction factor Fa equals 1.2 for steady load, e.g. centrifugal pumps, fans, light machines, tools, conveyors. Power transmitted by belt for design purpose, kW, max. Equals 1.308. Equals 1.5707 W. The power transmitting capacities of belt are developed for 180 of arc of contact. The actual arc of contact will be different in different applications. Angle of wrap for driving wheel equals 230. Therefore, FD equals 0.86, from design data book. KO corrected equals, KW, max FD. KO corrected equals 1.35 W. High-speed duck belting is selected for general purpose applications. Corrected KW rating equals 0.1216 W. Now, width no applies, equals 11.101. Therefore, selecting no applies equals 3 and width of belt equals 7 mm. Model, the platform rotates on the rail, with the help of wheel. The wheel is connected to the motor. After giving power supply to the motor, the wheel rotates from the inner side of the rail. The outer side of rail is supported by two bearings, which is exactly opposite to the wheel placement. A belt runs over these two bearings and in this way the stand rotates smoothly. When the object is placed between two pointers, the upper flutes can be adjusted as per the object's size. In this way, the complete system is brought to scan the object. The scanner rotates around the object and scans the necessary data points. A 3D model was created using 3D Experience platform for a better visualization and understanding using the dimensions of parts found after calculations. Figure 9 3D model of the mechanism. For analysis. Analysis was carried out using Simulia apps from 3D Experience software. The main apps used were part design, structural scenario creation, mechanical scenario creation, physics results explorer. As only the lower pointer will be under load, simulation was done for only that part. This pointer will only support the load of the objects, so, accordingly a mechanical scenario was created and results were explored. 1. Outcome of analysis. After the analysis on the lower pointer was done, it was found that stresses on the pointer were negligible and that the design was safe. Figure 10 Appling loads. Figure 11 Meshing. Figure 12 Simulation results. V. Actual scanning of the object. Objects were scanned using a 3D scanner Intel SR RealSense 300. The software used are Intel RealSense, 3D Sense, 3D PLM. The scanned data was collected using the RealSense software. Then the data was imported in 3D Sense, which can save the image. The scanner was moved by hand while scanning these objects, and as it can be seen clearly in figure, the images are missing some parts of the object. If the object is scanned using the proposed mechanism, the accuracy of scanning can be improved drastically. Figure 13 Objects and their scanned images. 6. Simulation of the scanning system. Mechanical system design of 3D Experience software was used to verify the system's working. According to the size of the object, the upper pointer was be adjusted. Some distance was to be maintained between the scanner and object. This distance can be different for different objects. When the object is larger in size, the scanner is away from its initial position and vice versa. Figure 14 Simulation of BMW wheel. Figure 15 Simulation of pepper crusher. 7 Summary. 1. When scanner motion is given by hand, the image is not complete. 2. Data points collected by the scanner are converted into an STL file in 3D sense. These points can be imported and optimized using the Function Generative Design app of 3D Experience platform, a Dassault Systemes platform, 3D PLM. 3. Objects should be held between 2 point supports so that maximum area of object can be captured. 4. Analysis was carried out using Simulia apps from 3D Experience software and the resultant was safe design.